Okay, so in this second part now, we're going to look at a type of problem to do with lift. So things that move up and down, but also the lift contains, say, people inside of it. So you've got multiple objects. Again, you've got the object of the whole elevator, but the elevator itself contains people, right? So we've got the elevator that's been pulled up by some ropes, tension, and then we've got people inside, right? So we've got some people inside, and they have their own sort of forces and their own masses and stuff like that. Now, this is a special type of problem because it requires the idea with certain type of forces, Newton's third law. Okay, this is the final law of we're going to look at. So we looked at the first two. As a reminder, the first law was basically if you move at a constant velocity, then that means the forces on you must be balanced. The second law was basically F equals ma. It's just an equation. The third law is, again, you might remember it as every action, you might have heard of it, every action has an equal but opposite reaction. Now, what that means is, I guess more in this context is, if two objects, A and B, interact with each other, or what we say in contact, then each object imposes or exerts, the more technical term, so it puts an equal but opposite force onto each other. Okay, what on earth does that mean? Let's try and have a look at an example of this Newton's third law in action. And I'm not the best at physics, unfortunately, but I'll try and give a sort of good enough example to try and hopefully make sense of this. So probably the most common example you maybe would have seen is, again, some sort of object on the floor, right? Object on the floor. So we've got this person, for example. Let's say we have a person standing on the floor. So the person is standing still here, right? And so you would have seen that firstly the person has a reaction force here, okay, against the floor to stop it from sinking down the floor due to the person's weight. Now, the floor then, so Newton's third law says when two objects are in contact with each other, so the person is in contact with the floor, that's saying that they create contact forces onto one another. Now, the reaction is the contact force put on the floor, put by the floor onto the person. So the floor exerts a reaction force onto the person. That's the contact force on the person in this instance. So when they meet, that's the force created on the person. What about the force created on the floor then? Well, the floor has a reaction, not a reaction. The floor has its own force, okay? Created by the person, inflicted by the person. I'll call that F of P, right? So the force created by the person which is acting on the floor, okay? So you can see that there's a force put on the person and a force put on the floor, okay? That are going to be equal but opposite directions. So these are the two forces that arise when the person is in contact with the floor, okay? Due to Newton's third law. There has to be these two contact forces as a result of them meeting. Okay, now, I said they're standing still, so there's going to be no acceleration. What am I going to say now? Well, now what I'm going to say is, what about if the person is jumping up and down? Okay, so let's say, again, have the same situation, the person here. Now, if they're jumping up and down, I'm gonna assume the instant the person jumps back and touches back on the ground. Okay, so when they come back on the ground, they're going to slow right down, right? Their speed is going to come right down. So let's say the acceleration is, let's say, -2. Okay, the minus meaning it's slowing down. Okay, that's what negative acceleration means. It's a deceleration. Okay, so in this instance, again, there will be a floor and the person. The person will create a force onto the floor, so the floor itself will have a force F of P. So again, a reaction, a contact force due to the meeting. So the contact force acting on the floor, and then the contact force acting on the person is again a reaction. Okay. So now they're going to be equal and opposite, but they're going to be different numbers because the acceleration is different here. Now think about this again, I guess more realistically. If you're standing still, are you going to be putting on the same force on the floor than if you're jumping up and down on the floor? I think if you're jumping up and down on the floor, I think you're going to be putting a lot more force and pressure onto the floor. Okay, so I expect the force here to be bigger than here. Okay, let's have a look at it then. And you'll see as well, the force created will not be weight necessarily. But let's go on to that now. If I was to consider if I was to draw the force diagram of just the person, okay, in this instance. So, as we discussed, there'll be a reaction force acting on the person by the floor, which is, there we are, the reaction. Now, the person will also feel its weight, okay? Now, I want to emphasize very clearly, the weight is not necessarily the same force FP here. The force FP, the force inflicted on the floor due to the person, so the contact force, the force is acting on the floor, okay? So it's not right to say F of P will be acting on the person because it's acting on the floor. The force is created by the person that's put onto the floor because they're in contact, okay? The weight of the person acts on the person, and the weight actually is independent to pretty much anything the person's doing because the weight is actually fixed. Because think about this, right? The weight is mass times G, right? Well, G is just a number, right? It's 9.8. So 9.8 lots of the person's mass. But the person's mass is mostly fixed. Obviously, they can lose weight and gain weight or whatever. But let's say the mass is 100, right? It's fixed in a sense that no matter what scenario you're in, you're kind of at the same mass no matter what. So the mass is 100. So let's say, just to keep it simple, so let's say the weight is 9.8 times 100. That's 980 newtons. So actually, that's saying no matter what, the person's weight is 980. Okay, so that's acting on the person. Then that makes sense again, because if the weight is always fixed, then it doesn't make sense for the force the person creating on the floor to be always 980. Because again, as we discussed, if you're jumping up and down, you're going to create more force onto the floor each time you hit the floor, right? So it doesn't make sense to be the same force every single time, no matter what you're doing to the floor, right? So anyway, so the weight acts on the person independent to any contact. So even if there's no contact between a floor and the person, there'd be no reaction force. Let's say it's falling through the air, so it's not in contact with anything. But there'll still be weight pulling it down at the end of the day, right? The weight is independent to any contact with the surface, okay? So the weight acts strictly on the person, downwards, okay? The reaction is caused by the floor, however, okay? That stops it sinking through the floor. Okay, so if I was to resolve, again, there's no acceleration because it's standing still on the floor. If we resolve upwards, let's say, well, the reaction force, take away the weight of 980 equals, well, it'd be 0, right? Because there's no acceleration. So therefore the reaction is equal to 980 here. So if I add that on, that's 980 newtons. And because of Newton's third law, because these two are contact forces due to them being in contact, they're meeting together, they're equal and opposite. So the force created by the floor is the same force here created by the person, which is 980 as well, but the opposite directions. Okay, let's take this example. So reaction in this case, it is the weight, okay, which I guess can make sense because you're not moving anywhere, so you're not creating any additional force. Okay, jumping up and down. Now it's slowing down, but now it's decelerating at -2 because it's hitting the floor, so it's going to lose its speed quite quickly. So in this case, if I draw the force diagram on the person, again, it's going to be the same diagram. The reaction force and its weight of 980. Again, the weight, I must stress, is independent to any contact. The person will have the same weight regardless where it's at, what situation it's in. So it's not the weight acting the weight is acting down on the person, not on the floor. Okay, the floor itself has its own force of F of P. Okay, so that's 100 kilograms. So it's decelerating, going down by -2. Now, if I was to use F equals ma here, if I resolve downwards where the acceleration is, so the weight of 980 take away the reaction is going to be the weight, the mass of 100 times -2 for the acceleration, which is -200, right? So therefore the reaction, if I solve this, is going to be 1180 newtons, okay? So that means the reaction up here is 1180. And now you can see the difference. Originally when they're standing still it's 980, but now when they're jumping up and down, they're creating more pressure and force on the floor when they're in contact. It's a higher number. So that means the force on the floor is also 1180 due to Newton's third law, because they're both contact forces arising when they meet, but they're put on by each other, so they're equal and opposite. Okay. So this actually makes sense because now I'm saying if I'm jumping on the floor, jumping up and down on the floor, I am putting more force onto the floor because of the contact, the person with the floor. So hopefully you can see it's not just the weight. If it was just the weight in this instance, it'd be 980. But that 980 is purely acting on the person, not on the floor. The force acting on the floor due to the contact with the person is different, it's higher. Again, because of this as jumping up and down, okay? And so there we are. That is the essence of Newton's third law. So Newton's third law, you create, whenever your two objects are in contact, so the person on the floor here, they create contact forces that act on one another. So the reaction force and the force on the floor there. Okay, and also hopefully you can see that it's not necessarily the force on the floor, not necessarily going to be the weight, because the weight is always fixed on the person no matter what. And the weight is always acting on the person, even if there is no contact, you'd still have weight. So it doesn't make sense for the weight to be the force on the floor, because the weight is on the person. The weight is the force independent of any of that on the person. Okay, so the person, no matter what, has 980 weight, regardless if it is meeting or touching a floor. And maybe to answer one more possible question people might have, the reason why so far and later on in the course we just say we ignore that force and just say the weight, right? The weight. The reason why we just use this force diagram, for example what we've seen so far, why don't we include this force on the floor as well? Well, because what we're doing in most mechanics problems is we only want to consider the forces on the person, okay? We don't care about any forces on the floor itself. This is a force on the floor, okay, created by the person. But we don't care about forces on the floor, so we kind of just ignore it and just look at the weight and the reaction of the person. So the force is specifically acting on the person. So technically, this whole time, yes, there's also a force acting on the floor when the person is on the floor. But we ignore it for mechanics problems because we don't care about that. We don't care about the forces on the floor. We care about the forces on the person. So technically, there's always been a contact force on the floor due to the person, but we ignore it because we only care about the forces on the person itself, which is its weight and its reaction. Okay, so that's Newton's third law. So again, hopefully that made some sort of sense. It's very, very tricky. I mean, I still find it very, very hard, this sort of concept. I'm not a physicist, but hopefully it sort of made sense. I don't know, but let's have a look at some examples with this in action. There's not many examples. It's not a common sort of thing they ask, but it's something you need to be aware of. So, okay, this example. So what we've got here is a light scale pan. So this little triangle here is attached to a light inextensible string, which is this top line here. Now, it's going to be tension in the string, right? Because it's being pulled down, right? This whole scale pan and the mass is inside of it. It's going to want to pull the whole thing down, right? But the tension then saying, no, you're stretching me, so I want to go upwards instead. Okay, so remember, tension opposes any stretching. So if it's being stretched down, the tension will go upwards to oppose it. Okay, and again, as we discussed, it carries two masses, A and B. And the mass of A is 400 grams and the mass of B is 600. A rests on top of B, as shown in the diagram. So A is directly on top of B. So we've got two different situations. We've got two different types of objects in contact with each other. So firstly, we've got A in contact with B. We've also got B in contact with the whole scale pan itself. Okay, so A is touching B and B is also touching the scale pan at the bottom here because it's resting on the scale pan. Okay, the scale pan is raised vertically, so it's going to move upwards with acceleration 0.5. Okay, so firstly, we want to find the tension in the string. Now, this is actually just connected particles that we looked at in the first half of the video. So if we want to find the tension, well, again, all the things are connected together, right? They're all connected as one. So A is on B, B is on the scale pan, and so they're all connected. And so essentially, the whole system is being connected by the tension. So if we consider the whole system, and again, all three objects, all three of them, the pan, A and B, are all moving upwards, so we can consider them as a whole. Well, okay, if we use F equals ma, if we resolve upwards, and then we've got the tension force, okay, take away. Now, the forces downwards, well, firstly, it'll be the weights, right? So the weights dragging A and B down. Well, the weight is mass times G, right? But remember, mass has to be in kilograms. The problem here is we've got 400 grams. That has to equal 0.4 kg. That's a standard unit, so that would be 0.4 times G. Okay, that's from A. That's the weight of A pulling it down. B also have a weight of 600 G, so it's going to be 0.6 G pulling it down. Okay, the scale pan has no mass because it's light. Remember, light means no mass. So the scale pan itself has no mass, so no weight coming from the pan. So these are the two forces pulling it down overall. Okay, so overall, tension is going against these two weights pulling it down. So T take away 0.4 G, take away 0.6 G is equal to MA. Well, the total mass, well, 400 grams or 600 grams, that's 1,000 grams. But remember, that would be 1 kilogram. So 1 times the acceleration of 0.5. So then we get T take away 1 G, or just G, or just 9.8 equals 0.5. So then at that point we get the tension. If we add 9.8, we get 10.3 newtons. So that's my tension. That's 10.3 there. Okay. For part B then, we want the force exerted on mass B by mass A. So again, we have mass B, but mass B is in contact with mass A because mass A is on top of mass B. They're touching, right? So we want the force exerted onto mass B. So if we consider mass of B, right? But firstly, B will have on its own will have just its weight pulling it down. That's going to be 0.6 lots of G. But there's going to be more forces if we just consider B on its own. So if we consider B on its own, so we're considering it separately, well, due to Newton's third law, because now we've got two objects here in contact, as a result of them being in contact, they create an equal but opposite force. Okay? So they will create or impose forces on each other. So A will create a force onto B, likewise B will create a force onto A. So if I draw A, just to help illustrate A on top of here, well, firstly A will exert or put on a force onto B. Now think about it, if A is on top of B and it's kind of in the air almost, A is going to want to push it down, right? If A is on top of B, it's kind of crushing down on B. So because of that, it creates, due to Newton's third law, A has to create a force on B. I don't know what that force is, but it's going to create a force onto B. And I'm going to call that force of A. Okay? So this force A is the force created by A onto B because A is in contact with B. That's not necessarily going to be its weight, okay? We don't know what the force is, but I do know they create a force due to their contact with each other, okay? Likewise, that's not the only force on B, okay? That's what I want to work out. Remember, what it wants me to work out is the force exerted on mass B by mass A. Well, F8 is that force created by A onto B. But that's not the only force, right? The other force is, you need to remember that B is also in contact with the scale pan because it's on the floor of the scale pan. So because it's on the floor of the scale pan as well, if I draw the floor, there's going to be a sort of reaction force. It's going to go up. So because B is also in contact with the floor, with the scale pan floor, the scale pan will also exert a force upwards to B as well. Okay? And I'm going to call that force S to mean the force of the scale pan. Force of the scale pan, SP. Okay, that's the force created by the scale pan onto B. So actually this is the full force diagram. So B by itself creates a weight force pulling it down as usual, but the other forces arise from B being in contact with A, but also B being in contact by the scale pan. I don't know what those two forces are, but I do know the force are created by B being in contact with them too. So the problem is, if I want to work out the force created by A, well, I need to work out what the force by the scale pan is. So I can't proceed really. What if instead I consider A? I know we're talking about what the force A goes on to B, but let's just consider what happens, the forces on A here. So A is here. Now A has a mass again by its own accord, pulling it down, that's 0.4 G, because the mass of A is 0.4 kilograms. Now, as we discussed, A is in contact with B. Okay? Now, B is sort of on this B, because A is on B, the B kind of creates the floor for A, because A is on B. So it's sort of like A is on the floor, but the floor is now B. The floor of B, right? It's on the surface of B. So it kind of creates, so the reaction, so the force that B creates onto A, so if this is B, right? The force that B creates onto A is sort of a reaction force, right? I'll call that force B. That's the force that B creates onto A. So remember, so that's the force that B exerts onto A. Now remember, the force that A exerts onto B is FA. The force that B exerts onto A is F of B. They're opposite. They're equal but opposite, right? F of A, the force created by A, is the same as the force created by B onto A and onto B, right? So this is the force diagram we've got, okay? And remember, A is not touching the scale pan. A is only touching B. So there is no considerations for A touching the scale pan. So that's all the forces. This I can work with because the only unknown is F of B. Okay, that's the force created by B touching A. Now, again, it's accelerating upwards of 0.5. Now, I need to work out what F of B is, right? So if I resolve upwards, that's going to be F of B, the force created by B, take away 0.4 G, equals MA. Well, A is 0.4 for mass, so 0.4 times 0.5. So F of B, take away 0.4 times 9.8 for G, is going to be 0.2. Okay, and so F of B, take away 3.92 is 0.2. So if I add on 3.92, I get the force created by B is 4.12 newtons. Okay, so there we are. So this is 4.12 newtons. Now, that's the force created by B onto A. That's the force B creates onto A, right? But I want the force exerted on B by A. I want the other way around. I don't want the force. I don't want the force created by B. I want the force created by A onto B instead. I want this force here. But as we discussed, Newton's third law says that these two forces have to be equal but opposite. Okay, these are the two contact forces due to B and A touching. So due to Newton's third law, F and FA has to FA and FB must be equal but opposite to it. Must be equal but opposite. Well, actually, just in terms of physical size, well, force of A has to be 4.12 newtons as well. So there we are. So that's the key thing to remember with these sort of questions. When you got two objects touching each other in contact in this way, they create equal but opposite. They create forces onto one another. Okay, so there we are. Then in part C, what's the force exerted by mass B on the scale pan? Okay, so if I go back to part B, I now know that the force created by A is 4.12. Well, it wants me to work out the force put onto mass B by the scale pan. Well, as we discussed, it's this force here. So actually, to do part C, again, it's going to accelerate up by 0.5. So if I just resolve upwards, then I can find this force F of SP, the force of the scale pan that's put onto B, which is what I want. So if I resolve upwards, I'll get F of SP, take away 0.6 G, take away 4.12, and that's going to equal MA. So it's going to equal the mass of B, which is 0.6 kilograms, times 0.5. Okay, so then if I solve for F of SP, take away, okay, so if I work all this out then, so F of SP, take away 0.6, lots of 9.8 for G, take away 4.12, I get minus 10. That equals 0.6 times 0.5, which is 0.3. Okay, therefore F of SP is 10 add 0.3, which is 10.3 newtons. So that's the force created by the scale pan onto B. Okay. Alternatively, what you could instead is consider, like I did with A and B, consider the scale pan in its own right as well. So the scale pan, remember, is this triangle, and then it has the tension force. Now the tension force in part A, so if we go back, the tension force is 10.3. Now, the scale pan is only in contact with B, right? This is B. Now think about it. What is the force that B creates onto the scale pan? Again, B is a mass. It's going to want to pull it down, kind of like its weight. So B is in contact with the scale pan. So again, B creates a contact force with the scale pan. I'll call this F of B. I should probably call f of b prime, okay, because we already use f of b. So a different force created by b, but now the force created by b to the scale pan when the b is in contact with the pan. So there we are, okay. And that's all the forces. So again, it's going to accelerate up by 0.5. So if I resolve upwards, so then 10.3 take away f of b prime equals, well, the mass is 0. As we discussed, it's light, so there's no mass with the pan. So it's 0. 0 times 0.5, well, that's just 0. So simply, the force imposed by B onto the scale pan here, the contact force created by B to the scale pan is 10.3. Well, what do you know? It's the same as 10.3 we worked out, okay? But they're opposite directions, okay? Due to Newton's third law, the force created by the scale pan to B is opposite to the force created by B onto the scale pan. They're in opposite directions, but they're equal, okay? So that's Newton's third law done, okay? Cool. So that's the idea, okay? Again, a lot to take in. It can be very conceptually difficult, right? Very, very difficult, okay? Let me practice with another question here. So here we're told two boxes A and B of masses 110 kilograms and 190 sit on the floor of a lift. So if I draw a lift, then perhaps looks like this. The lift is supported by a light inextensible cable, which looks again, it's going to be a cable upwards. There's gonna now we've got A and B, so again very similar to pretty identical to the last question. We have B and A sitting on top of it, right? So this is A. The mass of A is 110 and the mass of B is 190. Now the tension is going to oppose all that weight, so it's going to go up. And that's really it. We're told it descends, so it's moving down now. That's probably the only difference. It's descending with acceleration 1.8. So there we are. It's going down instead. But the rest of the question is the same as the last one, pretty much. Okay, so it wants for part A to work out the tension in the cable. Okay. So again, if because it's a connected system, that all the lift and the two particles are all going to move down, and they're connected because they're all in contact with one another, and they're all connected by the same tension in the string here. So they're all connected, they're all going down the same direction. We can consider it as a whole. So the whole system then, we don't need, because with the whole system, we don't need to consider all the individual contact forces. The contact forces created by A and B touching, and the contact forces created by B and the lift, because they're all equal and opposite. So they all cancel each other out if we consider it as a whole. So as a whole, we only got their individual forces, which are their two weights. So A has a weight of 110 G, and B has a weight of 190 G. They're not contact forces, they're just their individual weights in their own rights, okay? The lift also, are we told the mass of the lift? Yes, the lift has its own mass. The lift is no longer light. The lift has a mass of 170 G. So 1,700 kilograms. So the weight of the lift as well is 1,700 G. Okay, so the mass of the lift, I'll make a note of it, is 1,700 kilograms. Okay, so hopefully you're with me with that diagram. So the whole system then, if I resolve downwards, because that's where it's going down, so we've got these three downward forces, these three individual weights. So it's going to be 190 G, add 110 G, add 1,700 G equals, well, no, sorry, take away the tension going the other way. Then that equals MA. So the total mass is 110 kilograms from A, add 190 kilograms from B, add 1,700 kilograms from the elevator, times by the acceleration of 1.8. Okay, so if we do that, we just simplify all of this. Okay, well, we get 19,600 take away T equals 3,600. Okay. So at that point we can solve for T quite simply by subtracting 3,600 onto 19,600 to get 16,000 there. Okay. Then in part B, it wants me to find the force exerted by box B. So box B is causing the force onto box A and the floor on the lift. So again, if I so we have the force B, the box B is in contact with both A and the lift, right? So if I want to consider the force exerted onto A firstly, let's consider A. So the force is just on A. Okay, well A again is we have 110 kilograms. So individually, before any contact forces, it's just its weight pulling it down, 110 G. Now A is in contact with B. It's on the floor. It's kind of on the floor. It's kind of on a floor, right? It's on the surface of B. It's on the surface of B. So if you think about it, B, if this is B, it's going to exert a sort of reaction type force, right? It's going to go upwards, okay? So that's the force it created by force B here, okay? So because when A and B are in contact, this is the contact force created by B put onto A, okay? Because A is on the surface of B. Again, not necessarily a reaction or anything like that, but that's the idea. It creates some sort of contact force. Remember, again, go back to Newton's third law. When two objects are in contact with each other, they always create a contact force and they go opposite directions, okay? So the force created by B goes up, okay? Now, this is quite simple to solve for B now, because again, it's going to accelerate downwards by 1.2. So if we use F equals ma, if we resolve downwards, well, the weight of A, take away the force created by B put onto A when it's in contact with one another, that's going to equal ma. So it's going to equal 110 times 1.2. Oh no, 1.8, sorry, 1.8 for acceleration. So times 1.8. So if we solve for the force here, F of B, so we get 1,078, take away F of B equals 198. So therefore F of B, if we subtract by 198, we get 880 newtons, okay? That's the force created by A, and no, that's the force created by the contact with B and A that B puts onto A. Okay, there we are. Then it wants the force the force arising from the contact from the scale pan. No, sorry, from the lift and B. Okay, so we want to consider the lift now. So the lift again is this whole square thing. It has a tension rope pulling it up. Now the tension we discussed is 16,000, so we can sub that in. Now B is sort of on the lift, right? So B again is going to create a sort of contact force going down, okay? So I'll call that F of B. I'll call that FB prime to distinguish from F of B in the first part here. So again, so the contact, because of the contact between B and the lift, B is kind of wanting to push the elevator down, so the contact force is going down. Likewise, also because of Newton's third law, the lift itself will exert a force upwards onto B as well. That will be the force of the lift. Okay, so you can see they're going to be opposite to each other. So these are two of the contact forces created by the contact of B and the lift. But they're opposite, right? They're going to be the same, but they're opposite directions, okay? So there we are. Again, they're contact forces. I don't know exactly what they are, but I know they are created due to the contact of the two objects here. Okay, so now that's the lift. Also, remember the lift has a weight. The lift is where was it? the lift is 1700 kilograms. So in addition, the lift itself has a weight pulling it down by 1700 G. So that's some more forces for the lift. So if I now resolve, and it's accelerating downwards by 1.8 again. So if I resolve downwards, that's going to be well, what the downward force is, well, this F of B prime, take away 1700 G, no, sorry, add 1700 G, take away the upwards force of 16,000 equals MA, well, the mass is 17,000, no, sorry, 1700 times the acceleration of 1.8. Okay, that's the lift. So if you just simplify this, so FB prime, and then if we do 1700 lots of 9.8, take away 16,000, we get 660 equals 3060. Okay, and there we are. So then FB prime, if I subtract 660, I get 2,400 newtons there. And that is the force then created or imposed by B onto the scale pan, onto the lift. I keep mixing the questions up. There we are. Okay. So that is the force exerted by B onto the floor of the lift there. Okay. So again, the key idea is that they're in, the objects are in contact, so they create contact forces onto each other. Okay. So there we are. And again, do not get confused. It's not necessarily weight. Weight is separate, right? Weight is kind of their individual forces. A contact force when they meet with one another. So when the B interacts with the lift, it creates a different force. It's a contact force, okay? Due to Newton's third law. Different to weight. Weight is kind of individual to the object itself, okay? But there we are. So we've got this final exam question here, which is to do, which is going to look at the second type of problem we looked at. So now we're told a vertical rope PQ, you can see here, has its end Q, so the end Q here attached to the top of a small lift. The lift has a mass of 40, so that means it's going to be 40 G down. So the weight of the lift is going to be 40 G, and it carries a block of mass 10. So the block will also have a mass of 10. Okay. In fact, I'm just going to draw it myself. Okay, I don't want to make it messy. Okay, so the lift has a mass of 40. So downwards of 40 G. That's the weight. Mass times G. The block has a mass of 10 G. No, a mass of 10, so the weight is 10 G, and so there we are. The other force is the tension. Now tension is going to try to oppose the stretching because of the whole thing going downwards, so the tension will act upwards there, and we're also told it's moved vertically, it's raised vertically, so it's going to accelerate upwards with the acceleration of 0.2. okay. So that's the acceleration, and that's really it. And there we are. Then it says, using the model to find the tension in the rope. So again, they're connected. They're all connected by the rope, and they're all moving upwards. So we can consider the whole system. And again, we can ignore any contact forces. There will be contact forces that arise from the block in contact with the lift. Okay, so if we ignore all those forces, the only if we resolve upwards, then because it's moving up, while the tension is up, take away the two weights, so take away 10 G, take away 40 G, which are acting downwards, right? These two forces acting down, equals MA. By the total mass, then, if we're considering the whole thing, combining it, well, the lift is 40 kilograms. The weight is the block is 10 kilograms, so overall it's 50. The 50 for the mass times acceleration 0.2. So if we simplify this, so 50 times 9.8, so we get T take away for 90 is equal to 10, right? That's there we are. So if we add 490 on, we get the tension to be 500 newtons. So that's the tension in the rope. Okay, cool. Then in part B, it now wants the magnitude of the force exerted on the block by the lift cage. So the lift cage, it puts on or exerts a force onto the block now. So if I want to consider the block, then, well, what are the forces on my block? Okay, so if I draw the block here, well, firstly, the mass is 10 kilograms. So by its own accord, it's going to have its weight pulling itself down by 10g. But it's also in contact with the lift. Now, the block is on the floor of the lift again, right? Again, look at the diagram here. The black block is on the floor, on the surface of the lift. So the lift, in response to that, there's a contact force, right? So the lift creates almost like a reaction force, but it creates a contact force upwards. I'll call the reaction of the lift. No, sorry, not reaction. The force of the lift. So FL, okay, force of the lift. Also, the lift itself will then obviously B, the particle, the block will create a force of the block going down the lift. But that's not part of the block. That's part of the lift. So these are the forces acting on the block. Okay, so the weight naturally from the block itself, but again the contact force that also arises from the lift and the block touching. So the force that is put by the lift onto the block. Okay, there'll also be a lift from the block onto the lift, but we're not considering the lift here, only the force is acting on the block. Okay, so the force acted on the block by the lift here. So if we, again, it's going to accelerate upwards by 0.2. So if we resolve upwards, then where we got this force from the lift FL onto the block, take away the weight of 10g, equals ma, when the mass is 10 times 0.2. So FL take away 10 times 9.8 is 98, equals 2. So FL is 100 newtons. So that is the force exerted on the block B by the lift. And so there we are. So that's it. So yeah, those are the main two sort of problems you need to be able to deal with. So you need to deal with questions involving towing. So maybe like a car that tows some sort of trailer or some other weight. They're connected by some towing bar. And also the second problem where you got objects in contact with each other. So here you got the block in contact with the lift, and we saw where we got the two masses on top of each other. So due to Newton's third law, remember, objects in contact with one another create forces on each other, contact forces when two objects meet. And due to Newton's third law as well, in addition to those contact forces, they're equal and opposite, okay, to each other. So there we are. I'll see you next time.